was getting the strategy.
No.
I want the doctor.
Who do you think is going to be the first kid to walk in, Mr. Brown?
You know, I was thinking about that. A lot of choices today.
I'll put my money on Ethan.
I want to say Alexa or Helen. All right, I'm going to bet on Helen today. Who's going to be the first one knocking at the door in minutes?
I put 4 cents on Ethan.
Well, technically, it was already done. It was Faith, technically.
Yeah, it was.
So, in reality, we've already determined who the first late student is. Now we're betting on who the second late student is. That's what we're going to go with?
Yeah.
You're special because you're late? There's another term for that, but we won't get into it. All right, ladies and gentlemen. So, which one would you rather? Would you rather know all the answers to questions you are asked, or would you rather be able to ask other people questions that they cannot answer? Jaslyn.
Know all the answers to the questions you are asked. Because maybe I'll pass that.
Good point. If you knew all the answers to questions you were asked, you would pass math class. You'd pass every class.
I agree.
Okay. All right, Victoria.
And I feel like if I didn't know the questions, like that many amount, like I feel like I'm gonna feel dumb. Like at least.
Wait a minute. Wait. So which one are you
For
picking?
the first one.
But you know the answers to all the
Right.
questions.
That's why I'm not picking the second one because I want to know all the answers so I don't feel dumb.
Okay, but now here's the question. And again, I'm not criticizing your choice. But imagine whenever you go up to somebody, I go up to Christian and I ask him a question, he can't answer it. And I'm like, well, the answer was obviously this. Right? Because you got to know the answers to the questions you're asking.
Super smart.
But that's the second one.
Oh.
You could go up to people and ask them a question that they do not know the answer to, but you do. Or you could simply, every time they ask you a question, you know the answer. Okay? Zoe?
The first one, because I could ask the question and I could be knowing the answer to the question even though I'm not in the class and I'm a previous.
Okay.
And I had the assignment and home or we was doing something and we missed the assignment for that day. We could know the answer to the question.
You would be everybody's lifeline.
And you could get and you can be an A+ student.
Well, you could be that anyway, but yes.
But if you know every question, you can pass every
It's
class
not
with
knowing
an A+.
every question, it's knowing the answer to every question.
I know.
Okay.
You can get an A+ on everything.
Alex, what are you thinking?
I want to know the answer.
Okay. You don't think it would be a burden at some point? People always calling you going, hey, we're having a debate about who hit, 3 home runs on opening day in 1999 for the Chicago Cubs. Puffy Rhodes, by the way, ladies and gentlemen. But anyway, that wouldn't be a problem for you?
I wouldn't tell people.
Oh, wait a minute. If you know the answers, you have to share the answers. Then how do you prove that you know the answers?
Just by answering them, right?
Well, that's what I mean. Do you have to answer? Someone asks you a question. Ooh, we've added a new level of complexity here. All right. What do you think, Kevin? Which one?
I say the second one.
Second one? Ask questions that nobody would know the answer to?
Yeah, because I don't know. I feel like quizzing everybody. I love quizzing everybody. I love teasing. That's my way of
Showing that I'm better than you.
No. But you already get it. I feel like it's too much of a burden. I feel like you know too much to the point where nobody wants to know.
Okay. All right, Kiana, what are you thinking?
The first option. But I would keep it a secret. I would tell no one, And I would.
Yeah, but every time you're asked a question, people will be, whenever I have a question and I can't answer it, I ask Kiana, and she always knows the answer.
No, I wouldn't answer them. I would lie to them. Be like, it's 12.
No, you can't do that.
Yes, I can.
Because then you're not showing that you know all the answers to the questions. If you lie.
If I know that I know.
Oh no, because you're going to claim you're doing that already now. Every one of you is going to be like, yeah, that's what I did on that last test. I knew all the answers, but I just didn't want to show you, so I got some of them wrong. No. You can't cheat that way. You know which one you want? You want the first one? You want to know all the answers? All right, Christian?
The first one.
Christian wants to know all the answers. All right, Ethan?
I would know all the answers.
You would know all the answers, everyone.
Yes, sir.
Good. Mariana? Know all the answers? Okay. All right, Lucy? Obviously, that's a better choice here, huh? Okay. Just to be a contrarian, I would probably go with the second one. Of course, that would be a bad thing for a teacher. Bad thing. Who is it?
Lost.
Dang it! I didn't have Brianna in the pool. Good morning. So, all right. We got a lot to get done today, ladies and gentlemen. It's looking like your test will be about a week from today, next week, Wednesday. Okay? So we're not going to have a quiz this week. That's the good news. Because the test is next week, Wednesday. It doesn't pay to have a quiz on Friday and then the test on Wednesday. So we're going to finish talking about some gas laws. So if you would, ladies and gentlemen, open up 3 things for me. One, open up your EISN. And in your EISN, please get to slide number 20. That's where we're going to start today. And then go into Google Classroom, ladies and gentlemen. And in Google Classroom, please open up the Gay-Lussac's Law worksheet. It is in the side over here under upcoming events. You can open it up there, ladies and gentlemen, or you can go into the classwork, and it's the top thing in the classwork. When you open this, ladies and gentlemen, there are 2 files that you need to open. One is a Google Sheets and one is a Google document. The reason for both is because obviously we're doing a lot of graphing with this because we're talking about relationships. So if you could open those both up. So just a reminder, again, for all of my classes, this is an amazing time of the year, ladies and gentlemen. Absolutely amazing. At this point, I have no one in any of my classes who is missing a quiz or a test. No one. Thank you guys for making it up if you missed, okay? So that is a good, unusual thing for me, okay? But there may be some of you who are still missing a lab activity. And if you're missing a lab activity, that is bringing your grade down. So get those done and get those turned in so that I can get your grade up to where it needs to be. Okay? Today we're going to talk about relationships in gas laws. What are the 2 kinds of relationships? Inverse and direct. That is the main one, inverse or direct. When you change something or variables, the things that you change, going in the same direction, meaning a direct relationship. Could be going up, could be going down. Or do you have an inverse relationship going on? One goes up, one goes down. We already talked about Boyle's Law. Which one was it?
Inverse.
Boyle's Law was an inverse. Yes, Boyle's Law was an inverse. Now, I don't know if we'll get to it today, but in the next 2 days, I will summarize all the gas laws for you, and then you could take and put them onto your periodic table so that you can remember which ones are which gas laws and what kind of relationships there are. But I'll show you a table that summarizes all of that in the next couple days. Okay?
Did we finish the thing that I was thinking yesterday?
We did finish the Boyle's Law Lab, yes. So if you were not here yesterday, the video is out there from yesterday morning. You can go to it, you can look at it, and it'll help you answer those questions. You could come and you could see me, and I could help you answer them during home base as well, just not today because we have a CRM lesson. So that Boyle's Law Lab, ladies and gentlemen, is due sometime before the end of the day today. Okay? A lot of you turned it in yesterday. Most of you turned it in yesterday. I was one off. Okay? One off.
That you're so confused.
What?
Nothing. Go ahead and have a seat. So, ladies and gentlemen, anyway, that we went through the stuff. Most of you turned it in. Good job. Those of you who weren't here, it's online. You can get to it and you can get it done. All right. Okay, so here we go, ladies and gentlemen. Yesterday, we left off with this thrilling lady telling us about Charles' Law. Okay? And she did the demonstration with the balloon where she poured liquid nitrogen on it and the balloon shrunk dramatically. Okay? That is because Charles' Law is about volume and temperature, and it is a direct relationship. Pressure and amount of gas are held constant. Now, a direct relationship, the variables are going to be divided. So V over T. volume divided by temperature. We're dividing these numbers, ladies and gentlemen, and then we get a K. We get a constant, a number that does not change. Doesn't matter what unit volume is in. V stands for volume. You can use milliliters, you can use liters, you can use cubic centimeters. The main thing is, though, volume needs to be in the same unit on both sides of this equation. Temperature, however, ladies and gentlemen, has to be in Kelvin. Kelvin was the scale that was the absolute scale, meaning it doesn't have any what? If it is an absolute scale, that means it has no what? What? Nope. Think of an absolute number in math. It is always what?
Constant.
No, it is not always constant, but it is always... yeah, I agree. It is always a number. What kind of number is it always?
Positive number.
What?
Positive number.
Thank you. It is always a positive number. Your values for Kelvin temperature will always be a positive number, and we're going to show you why that's important today. Okay? So this is Charles' law, ladies and gentlemen. Okay, now, open up this worksheet, ladies and gentlemen. This worksheet, open it up. We are going to fill in these two tables up here in just a second, ladies and gentlemen. But to help us along, I have a Google Sheet where we are going to put in our information so we can put it into here, ladies and gentlemen, and then we will simply copy these tables down and put them into the other, into your worksheet. So actually, even though it's on the worksheet, this is where we need to be to start out. So open up this, ladies and gentlemen, so that we can collect these numbers here. Now, here's a wonderful part about a Google Sheet, ladies and gentlemen. We can set a formula so that it is going to give us pressure divided by temperature as a constant. Okay? So it's going to take whatever number we put in here, pressure divided by temperature, and it's going to do the division for us right away. The reason that it's this right now is I don't have any numbers in here. That'll take care of itself in a minute. Okay? All right. So to help us out here, ladies and gentlemen, we're going to use this FET that we looked at the other day. To do this, though, we are changing only two things. We are changing the temperature and we are changing the pressure. Yes. Certainly, sir. I will go grab one for you. So, get this, ladies and gentlemen, if you want to pull this up on your computer, in the worksheet where it says class demo highlighted in blue, that is a link to this if you want to go to it. You do not have to, but if you want to.
I'm confused.
You go to the worksheet. Yep, the first one.
There you go. Okay. So, one of the things we need to do with this, because we do not want volume to change, ladies and gentlemen, I'm going to click on this lock button here. Okay? What that lock button is going to do is make it so that this volume will not change for us. It will stay the same throughout the entire experiment, which is what happens in Gay-Lussac's law, because he dealt with pressure and temperature. He left the volume constant. Okay? Now, if you wanted to add more gas, you could pump the handle here. It would put more gas inside there. We don't need to. There's a gas inside there already bouncing around, hitting things. Okay? So, give me a temperature. Pick a number between 150 and 600. A higher number.
600.
Okay, let's go to 600. So we're going to heat this up till we get to around 600 degrees. Perfect. Excellent. Wonderful. The pressure is 1.85 atm, ladies and gentlemen. So we are going to go into here. First of all, I'm going to change something because this unit is not correct. I'm going to change kPa to atm. Let's change that on both of these, please. All right, so our pressure is 1.85 atm at a temperature of 600. So in here, we're going to do 600 Kelvin because that's the temperature it's reading it, and we're going to do 1.85. Okay? How do I get temperature in degrees Celsius? Good. Somebody grab a calculator. I have tons of them up here, and you do that calculation for me real quick. Okay? Now, what is the same over here is the 1.85. Okay? All I'm doing is taking the temperature and converting it back into Celsius. So somebody could give that to me, please. Come on, minus 273. You got calculators, you got computers, you got brains. All of those things could be used this morning, ladies and gentlemen. Uh-oh, somebody's in trouble. Mr. Brand. Which one?
No, I don't need to go.
Okay, Ethan B. Okay.
Ooh,
Okay.
you in trouble.
Ethan's in trouble. Okay, good. So suspension. What? What? Okay, thank you. All right, bye.
Ah.
Grab your stuff. You're out of here.
Ooh.
Ooh, all together now.
Ooh.
You people suck at this game. Come on, one time, all together now. Ooh, thank you. Let's go. Let's go. Principals are waiting for you. No. Career Center. Go down to see Miss.
Why you gotta ruin the fun, Mr. Brand?
What?
So why you gotta ruin the fun?
Well, I got to tell him where he's going. I can't lie to him about that. He gets down by the principals. They're like, why did he send you down here? Okay, what do we got for a temperature? Come on. Minus 273. What?
Just 600 minus 200.
600 minus 273. 327. Excellent. All right. So now I need another temperature. Give me another temperature, ladies and gentlemen. Lower. Give me another number.
493.
I can't do 493. It won't let me do that. I'll do around 490 though. Look here. It's just like raining students outside. 490. How about that? We'll try to get close to that. All right. There we go. There we go. That's it. You're getting 485. Sorry, ain't getting any closer. 1.49 atmospheres. What was the temp? 485. 1 point what? You guys suck at remembering these things. 49. 49. Hey, Ethan, it was a lot quieter before you got here. Okay, take out your computer, get to work. Come on, open up your stuff. Thank you. All right, I need somebody to subtract 273 from that to give me the temperature. What do we got when we subtract 273? 485 minus 273.
212.
Very good, 212. All right, I need another temperature, ladies and gentlemen. What do we want to go down to?
300.
Let's not go that low yet because I don't know if I can get much lower than that. Let's go somewhere in between there. Between 485 and 300. 350.
That's what I was gonna think.
Ooh. There we go. Perfect. 1.08. 1.08 is our pressure. 350 is our temperature. 1.08 is still our pressure here. Somebody do the math. Minus 273. What do we get? 77. Thank you, Kiana. All right. Now I can go lower than 300. How low do you want to go? 200? 200 sound good?
Yeah.
Okay, let's go 200. 205 is as good as we're going to get. 0.63, ladies and gentlemen. 0.63 at 205. 0.63. Ooh, what the heck was that? All right, I need the temperature, please. Negative 60 what? Thank you. Very good. Perfect. Okay. Now, take a look here, ladies and gentlemen. Look at our constants. What does it mean to be a constant? Always be the same. Is this a constant? No, it is not. It is not a constant, ladies and gentlemen. Okay? Our temperatures are in degrees Celsius. These numbers are not even all positive, let alone the same. The last one is a negative number, right?
Right.
But look over here when we use Kelvin.
It's all the same.
That is a constant, ladies and gentlemen. That is a constant, okay? And that is what happens with gas laws when you use temperature in Kelvin. Now, I do want, yes, sir, go ahead.
So is there like a right and wrong to it then?
Well, what I'm saying is the only way we can use this gas law to create a true constant is we have to convert our temperatures into Kelvin. They must be in Kelvin. If we do them in Celsius, we do not get a true constant. Okay? All right? So that is why we have to do them that way. Now, please understand this. What is happening to temperature here? Going down. What's happening to pressure? What kind of relationship? Good. Remember, that's what we're going to concentrate on in here. That is a direct relationship. Even in Kelvin, what is happening to temperature? Going down. Pressure, still a direct relationship. Just like Charles' law with volume and temperature, Gay-Lussac's law with pressure and temperature is a direct relationship. Now, here's what you're going to do, ladies and gentlemen. You're going to highlight all of these numbers right here. For this second table, you're going to hit Control-C. Now you're going to go into this worksheet, and this is that second table, ladies and gentlemen, and we are going to do Control-V in here, and all our numbers get put in for us. The only thing we need to change is our pressure is in ATM right now. Pressure is in ATM. Now we go back and we highlight the other table, just the numbers. Control-C, into our worksheet, Control-V. Okay, now back to our Google Sheet. I'll give you a second to get caught up. I realize some of you may not type as fast as I do.
Copy the whole thing.
Okay, so let me ask you this. What are we expecting the graph of pressure temperature to look like? Just think about that for a minute. What do our graphs look like? Okay, which means what? Okay, should be a straight line. Which means what? It's going up. Okay? So if we have a direct relationship, the line should be going up. If it is a constant, it should be straight. Let's see what our lines look like, ladies and gentlemen. Let's start with Celsius. What do you notice about the line? It is straight. Even though there is not a constant, a K value that is the same here, this is still a straight line, ladies and gentlemen. And you'll notice I'm in the below zero range, right? Okay. Did I talk to you guys about absolute zero? No? Yes? Maybe? Okay. What is the lowest temperature you can have in Kelvin? No, that's Celsius. In Kelvin, 0. We call that temperature absolute zero, meaning that is as cold as it can ever get. Okay? Now we got to think about something. What does temperature actually measure about a substance? What kind of energy? Kinetic. So what's the lowest amount of kinetic energy you could ever have? 0. None. But what does that mean for that substance if you have no kinetic energy? No, think about kinetic energy. Thank you. It's not moving. It's not moving. Now again, you may not remember this, but a long time ago we told you that there were 2 points to what is called kinetic molecular theory. All matter is made up of tiny particles. This desk is actually made up of tiny particles. And those particles are always what? Moving. The time when they will not move is if we get them to absolute zero. If we get them so cold that we take literally all of their energy away. By the way, we have never been able to do this. Never. And even in space, outer space, where it is incredibly cold, with nothing around, no gases, a vacuum, empty space, the temperature is still 2.57 Kelvin. It's still not absolute zero. So in science, absolute zero exists, but we have never gotten anything to it. So we don't know what will happen to this matter if we get it to absolute zero. We don't know what will happen to particles if we stop them from moving. Will they just stop? And then if we add a little heat, they'll start moving again, or will something happen to them? We don't know. But we can't tell what temperature absolute zero is. And how can we tell what temperature absolute zero is? Because this is a what kind of line? Straight. And I could take it all the way back to here until I cross the x-axis. And the point where I cross the x-axis, minus 273 degrees Celsius, 0 Kelvin. 0 Kelvin. We have proven that what that point should be. We just have never gotten to it. Okay? We've proven that point. Hit copy chart. Okay? Hit copy chart. Go into your worksheet. Control V. Paste it. There it is, ladies and gentlemen. Okay? Oops. What did I forget to change? I forgot to change the one label. That one label should be, instead of KPA, it should be what? I'm going to go and I'm going to change it. Okay. Now, here's the nice part. I do not have to re-paste this graph. I will simply hit update. By the way, I don't know why it is with Google, ladies and gentlemen. When we pasted that graph in here, it was not real clear, was it? Really tiny, hard to read. When we do this, boom, this is easy to read. Okay, this is easy to read. Okay, I don't know why Google does that all the time, but they do. All right, go back into the Google Sheet. Click on the one that says pressure and temperature in Kelvin. Copy the chart. I'm going to bring it in here. Control V. Paste. Now, I purposely forgot to change the pressure because now I want to go back in here. I want to change the pressure. If you did it ahead of time, that's okay. I'm going to change it to ATM, and it's going to make me a much nicer graph in here when I update it. Okay? When I update it. Questions? All right. Is there anyone who needs help or needs more time with that top part of the Google Sheet? I'm sorry, the document. Okay.
Got that part.
You got that part? Good. Good.
So for the second graph, do we need to change anything? Just the pressure?
Just the unit on the pressure. I'm not going to worry about the titles, just the unit on the pressure. Okay? Gentlemen, if you need to keep talking, separate. Okay? So, if you want to talk, you can do it, just not on my dime here. Okay? There are people who are trying to get things done and it's trying to get finished. Okay? So, all right. We good, Victoria?
Yeah.
Okay. All right. So now, ladies and gentlemen, let's go back into our EISN for a minute. Get to slide number 22. Actually, you get to slide number 22. I'm going to stop at slide number 21 for a minute. Volume and temperature. A direct relationship. Look at the graphs. What are they doing? Up. That is always a direct relationship. What kind of lines are they? What is their shape? Straight, meaning again a constant and a direct relationship, ladies and gentlemen. So, Boyle's law was an inverse. Charles' law is a direct. Gay-Lussac's law is a direct, ladies and gentlemen. We just showed that. Here's what Gay-Lussac's law says. The pressure of a gas will vary directly to its Kelvin temperature at a constant volume. Okay? At a constant volume, it will vary directly. But it's the Kelvin temperature. Pressure and temperature are in the direct relationship. One goes up, the other goes up. Okay? Volume and amount of gas have to be held constant. Again, the easiest way to see how one variable affects another is you only change one thing. You only change temperature and you see how pressure reacts to it. But to do that, you got to hold the other things constant. And remember, for gases, there are always four things. Always four things that we are talking about. Pressure, temperature, volume, and amount of gas. If we want to see how this and this react, these have to be constant. In every gas law we have done so far, we have looked at two of these and held the two others constant. And what one has been constant in every single gas law so far? Nope, not pressure, not volume. We're not keeping pressure constant here.
Gases.
The amount of gas. Thank you, Zoe. The amount of gas. Okay? All right. So, again, P over T equals a constant K. Pressure divided by temperature equals some number. So because of that, ladies and gentlemen, P1 over T1 is equal to P2 over T2. Now again, I am not going to make you do calculations with this, but I do expect you to be able to predict what will happen. Okay? I do expect you to predict what will happen. So keep this in mind, ladies and gentlemen. Pressure, temperature, a direct relationship. P1 over T1 equals P2 over T2. Okay? So, Ethan, I'm not going to tell you again. I understand that. But again, I'm not asking you to apologize. I'm just asking you to correct the behavior. Okay? Thank you. Okay? So, ladies and gentlemen, what would happen in this if pressure goes up? What's temperature going to do? Alex, temperature has to go up because they are in a direct relationship. That is the kind of question that I will ask you. If temperature goes down, what happens to pressure? What happens to pressure, Lucy? If temperature goes down, pressure goes down. Direct relationship. Okay? That's the kind of thing that I will be asking you on a quiz. That's the kind of thing I will be asking you on a test. If temperature were to go up, what would happen to pressure, Christopher? If temperature were to go up, what would happen to pressure? In a direct relationship? Okay, so that's the point. We got to know what kind of relationship it is. Questions? Okay, now, I want to do something very simple. Let's pick a nice, easy pressure. 10 psi. Okay? And we're going to do a temperature. Well, let's do this. If we go to 20 psi, what happens to our pressure here? What happened to our pressure here? It doubled. It is 2 times larger. Can we agree on that?
Yes.
So what has to happen to our temperature down here? If our top doubles, what has to happen to our bottom?
Double.
It has to double as well. Very good. Very good. So these temperatures, T1 and T2, would have to double, correct?
Correct.
Okay. Well, think about this for a minute. A few days ago, last week, we had snow last week, Wednesday, correct?
Correct.
So the temperature outside was probably, well, let's say we got to get out of Fahrenheit though. Let's go into Celsius. Let's say the temperature outside was 1 degree Celsius, just above freezing. Okay. Now, today it's about 44 degrees Celsius. So let's say it's 47.
Yeah.
It's supposed to be 68 this afternoon. Okay. Foiled by my own computer. If our temperature went from 1 degree Celsius to 4 degrees Celsius, how much of a change is that? But how many times larger? This is not hard math. 1 degree to 4 degree. What do you multiply 1 by to get to 4?
4.
It's 4 times change, right? 4 times change. What if we went from 1 degree Celsius to 10 degrees Celsius? Times 10. 10 times change, right? If our temperature changed 4 times, what would happen to our pressure? How much?
10 times.
Well, over here, pressure would go up 10 times. Over here, pressure would go up 4 times. So imagine, ladies and gentlemen, we talked about that bar, that 15 pounds of pressure per square inch on our body. On a cold day, if it went from 1 degree Celsius to 10 degrees Celsius, the air pressure around us would increase 10 times. 10 times. It would go from 1.5 or 15 psi to 150 psi. Guess what that could do to us?
Kill us.
If the pressure got too high, yeah, it could. It'd be like going too far down underwater. That would be creating more pressure on you. But, ladies and gentlemen, what is this temperature here in Kelvin? 1 degree Celsius, what is that in Kelvin? Degrees Celsius plus 273. What is this temperature? 274. What is 4 degrees in Kelvin? $277. Has this gone up 4 times? No, not even close. Not even close. This has gone up about 1/100th. This is a lot smaller change than this is. That is the other reason that we work gas laws in Kelvin. This change would be a dramatic change. This is not. Okay? So around the temperatures we live in, this is not a big change. Now granted, if you go from 1 Kelvin to 4 Kelvin, you're going to have a 4 times pressure increase. But guess what? At 1 Kelvin, there ain't very much pressure because the particles aren't moving very fast. Okay? The particles are not moving very fast. So they cannot create a lot of pressure. This is why, ladies and gentlemen, we have to work problems in Kelvin. This goes from 274 to 283. That is not a 10 times increase. That does not kill us under the pressure of a hot sunny day. Because the temperature change goes up 20 degrees than it did a day ago. Okay? In Kelvin, it is not as big a change. We have to put our numbers into Kelvin. Okay? All right, ladies and gentlemen, here's what I want you to do. Take a look at your worksheet. Okay? You are going to answer these questions about the graphs that you just put in. By the way, both graphs, which way is the line going? What kind of line is it? Straight. So it doesn't matter which graph you use. Okay? Either one you can use. Okay? Now, I want to show you how to do number 4. A gas has a pressure of 1.32 atmospheres at a temperature of 45.3 degrees Celsius. If the temperature is raised to 95.3, tell what would happen to the pressure of the gas. Would it increase or would it decrease? So, a couple of things. Number 1, I want you to practice converting from Celsius to Kelvin. How do we get from Celsius to Kelvin?
We add
What? 273. So you're going to take and you're going to convert both of these temperatures into Kelvin. But in these 2 yellow boxes, you are only going to put one of 2 things. Increase or decrease. Increase or decrease? Now, the change happens to temperature here. We go from this to this, okay? Because I'm given two temperatures. So to go from 45.3 to 95.3, what's happening to temperature here? It is increasing. So in this box, you're going to put increase. Now you are going to predict what will happen to the pressure if the temperature increases. So according to Gay-Lussac's law, pressure and temperature in a... So if this increases, what does this do? Increase. They both go the same direction. They both go the same direction. So that is what I am asking you to do here. Okay?
So for then the other two boxes, it would be decrease.
No. The other two boxes are not in play. Let me explain why.
Black ones.
We don't know what the change is to pressure because it doesn't tell us what the new pressure is.
So you don't put nothing in.
So we don't put nothing in here. And we can't predict the change in temperature because we already know what it is. The temperature did what? It increased. So in other words, the prediction is saying this is what should happen to the one that we would be solving for. In this case, we are solving for the pressure. What happened to the pressure? Did it go up or down? So that is our prediction. The change, we know what's happening to temperature because we're given both numbers. Here's what it is originally. Here's what the new one is. Okay? So if you go to the next one, ladies and gentlemen, again, the change is in the temperature. What's going to happen to the pressure? And again, convert the temperatures into Kelvin. So, direct relationship, remember they should always go in the same direction. Okay? Same direction. So, here, I'm giving you the change in pressure. If you look at the problem, it'll tell you the pressure was this and it goes to this. What's it doing? Then you can predict what should happen to the temperature. But I'm not making you find the new temperature here. That's why you don't have a second one to convert. Okay? That's why you do not have a second one to convert. Okay? So take a few minutes, ladies and gentlemen. Work on this worksheet. If you have questions, you can let me know. I will gladly come around and give you a hand. If you have questions about yesterday's lab, now would be the great time to ask them as well. Okay? Please don't forget to add the numbers here. Okay. Formula you need. Temperature in Kelvin is equal to the degrees Celsius temp plus 273. We did Boyle's Law lab. We did pressure and volume. We had syringes. We changed the pressure. We found the volume.
Oh, is it the connector?
It's a syringe connected to a pressure sensor. You can change the volume of the syringe and the pressure goes up. So we did that one yesterday to introduce gas laws. Then we talked about Charles' Law. Now we got Avogadro's and then Gay-Lussac's. And I'm going to mention Avogadro's as well. So that was the one that we did. A lot of times I would do this as a demo with dry ice and stuff. I just didn't have a chance to go out and get dry ice to do it. I'll do boiling water, dry ice, and cold water, but it's just as easy to use the FETs nowadays because the numbers come out exact. So,
The driest.
It is. But again, the advantage of doing it with a FET is we got a perfect constant. We normally don't get that with dry ice. We get pretty close. And even with the dry ice, we get it down to minus 273 as the temperature for predicted temperature.
Is that correct?
So, yes.
And then these two would be increase.
They increased, didn't it?
Yeah.
He's here to watch me. You're watching me.
Can you just add, we're adding 275
273. Well, it makes a difference, guys. There's a difference between being right and wrong. Okay. Which one? Okay, so go up and find the original temperature. In the problem, read the problem, what's the original temperature?
Why did you order freezer?
So what's happening? Okay, one has to have the pressure.
I was listening to it in there, but
Bad as hell.
Dude,
no, I'm getting it.
That is the relationship. The relationship says, I don't care which one you take, pressure or temperature.
I'm like,
You put
this law and then the
Charles and Boyle's law, yes. Yeah, definitely.
All I need is the question for the lab from yesterday. We answered the question, that's all.
Okay. So are you done with the worksheet today?
Yeah,
Okay. So here's your two graphs. You have your two graphs in here?
yes.
So graph number 1. Is that an inverse or a direct? Which way is the line going?
I can go this.
Okay. And is it constant or non-constant?
Constant.
Why is it constant?
Oh, non-constant.
Why is it non-constant?
Because it, like, curving going down.
Okay. So curving means non-constant, going down means inverse. So now you can answer that question in graph 1. What kind of relationship is it? Inverse or direct? Constant or non-constant? I'll be back to look at question 2. All right? All right. Yes, you are. Yep. Just do the math. Just do the math. All the negative temperature means, ladies and gentlemen, is Celsius, is that your temperature in Kelvin is going to be below 273. That's all it means. Okay? Now, please understand, if the temperature goes down in Celsius, what has to happen to the temperature in Kelvin? No. It's got, all we're doing is taking a number and adding 273 to it. So if we add 273 to this number, 273 to this number, whatever those original numbers did, that's still what's going to happen in Kelvin. Okay? So with this law, it is saying whatever change you make to either pressure or temperature, the other one is going to do the same thing. If temperature goes up, pressure goes up. Temperature goes down, pressure goes down. Pressure goes up, temperature goes up. Pressure goes down, temperature goes down. That is what a direct relationship is. Now we could take that exact same statement and do it with Charles' law. Volume goes up, temp goes up. Volume goes down, temp goes down. Temp goes up, volume has to go up. Temp goes down, volume goes down. In a direct relationship, whatever direction one variable goes, the other has to be the same. By the way, in Charles' law, temperature must be in what unit? Kelvin. In Kelvin. Okay? To work the gas laws, it must be in Kelvin. Not to understand the relationship, but if we were to solve the problem. Okay? Did you get the second part of that lab question, Zoe?
Yes.
Okay, so
No, I'm
which
trying
question?
to put what I got for 20.
Can we turn it in, Mr. Brand?
The worksheet?
Yeah.
If you're done, yes. Ignore the 20. Take that one out.
Alright.
Get rid of that. Ah! Hold on, hold on. Okay, that's fine. Just leave it there. Okay. Compare those numbers. No way, Zoe. You cannot take 50 times this number and get that
So
one.
when I
Go back to that chart.
when I got the,
Go back to that. Go. Erase all those numbers. Those are not pressure times volume.
Oh,
You need to take 50 times 123.4 and figure out what number you get there. Okay? You can't copy it out of that table. It's not the same table. Jimena.
Yeah. Wait, hey.
So, if you go from 404 to 55 mmHg to 225, what's happening? That's the only thing. Okay? So, ladies and gentlemen, when you read these problems, this one here, we're going to take a look at it real quick. This last one. .50 liters. Which one of these four is 8.50 liters, Alex? Is it a pressure, a temperature, a volume, or an amount of gas? It's a volume. Why? Because it's in liters. This is a volume. 90 or 455 mmHg. Ethan, what is that? 455 mmHg is a volume?
Oh, man, it's like for pressure, unit for pressure.
Okay, so what is this representing? A what?
Volume.
No. You just told me mmHg is the unit for what?
Pressure.
So what is this number telling you? Yeah. The point is the units are going to help tell you what that number is representing. 95 degrees Celsius. Jaslyn, what is that representing of these four? Pressure, temperature, volume, or amount of gas? Temperature, because degrees Celsius measures temperature. Okay. 225 mmHg. Victoria, 225 mmHg. What is that?
MMHG. What is it?
Pressure, volume, temperature, amount of gas.
Pressure.
It's a pressure. Okay, so here's a pressure. Here's a pressure. What is pressure doing? It's going down. That's what we're asking you to do when you read these problems. Find out what pressure is doing so that you can put it in here. Then you should be able to predict what temperature would do because pressure did what it did. Okay? So in these problems, you got to figure out what those numbers are representing. Are they representing a pressure? Are they representing a temperature? Are they representing a volume? Now again, this worksheet is all about pressure and temperature. So you should be able to find that. Should be able to find that. Questions?
so number 3 would be the variable.
Zoe, do you have a question?
So number 3 would be like the variable of one of the other.
Okay, in the lab,
Right.
what were the things that we changed? Variables are what we changed. What did we change?
The amount of pressure.
And of those four things up there, pressure, temperature, volume, and amount of gas, which two did we change in this lab?
Pressure and amount of gas.
We changed the amount of gas?
The pressure.
Look at your table. What's changing in your table?
And the volume.
Okay, so then those have to be the variables that we changed. The constants have to be the other two. Okay?
Are we doing questions? Yeah. Here. First here.
Yep. Okay. Okay, so now tell me what's happening to the pressure in this problem.
Well, let's see.
From what to what? To that's pressure going down. So in that box, put down that it's decreasing. Then what would that mean for temperature? Very good. Very good. Yes. That is what we are going to be doing in this unit. We're not going to ask you to calculate what the new temperature is. We're going to ask you to predict what the new temperature will be. That is as far as we will go with these as far as calculations go. Okay?
Do you think problem 5 will be different? Problem 5? Because of Celsius is 16.2 and the other one is -4. Yeah. And the first one's increasing. It's like we're not talking about like others gonna be.
Yep, I heard that.
You know, like pressure and temperature reaction towards each other.
I was getting caught up.
All right, ladies and gentlemen. Anyone need more time with the worksheet? Please make sure you turn it in then. It's not due till tomorrow, but again, if you're done, if you're finished with it, turn it in, get it out of the way, and be done with it. All right. So, Avogadro's law. There's one more law that we're going to cover today, and that is Avogadro's law. Now again, all of this time, we have been dealing with these 4 variables. Pressure, temperature, volume.
Should we write that on everybody?
No, you've already got this. At least you better have. This is what we started the unit with.
Ah.
An amount of gas. Okay. Here's our last gas law for the day, ladies and gentlemen. You ready? Would help if you'd look up.
A balloon.
This, ladies and gentlemen, is Avogadro's law. Now, you tell me, what did I change? What? Where, how did I change the pressure? Okay, so what did I change? What? I changed the amount of gas. That's for sure, correct? Didn't I put air inside the balloon? Isn't that a change? You're looking at me like I'm still from outer space, Faith.
Yeah.
Nope.
What-
By the way, what is the pressure like inside the balloon and outside?
The same.
Why?
It's
No.
You said what?
I asked what the pressure like inside the balloon and outside the balloon is. Zoe said the same. I asked why. How do we know it's the same?
Because it's still pushing like how it was.
it's the same air all around us.
I don't care that it's the same air. The other day, go ahead.
It's the same temperature.
Okay, it is the same temperature, good, but I don't care that it's the same temperature. Do you remember the other day when I had the glass jar up here? And the metal base?
Yeah.
We took the air out of the glass jar, right? Creating an area of what kind of pressure? Okay, low pressure. Let's just say low. I don't know if I got technically all the air out or not. So when I lifted it up, what happened? They stuck together. Why did I tell you they were stuck together?
Because the air outside was pushed.
The pressure was trying to get in.
Yeah, pressure.
What pressure was trying to get in?
Outside the low pressure.
Slow down. Inside was what kind of pressure?
Low pressure.
Outside was
High
high pressure. High pressure was trying to get in and take the spot of that low pressure, correct? Do you remember then I put the balloon inside it?
Yeah.
When I put the balloon inside of it and then we took away the air, what happened to the balloon?
Got smaller. Or
Got
bigger.
bigger.
It got bigger. Why?
It's trying to go to the low pressure.
High pressure always tries to fill in low pressure. The balloon got bigger because it was high pressure, right? How do we know the pressure inside and outside are equal?
Isn't trying escaping.
Well, it may be, but I don't know that for sure.
It could be constant.
It doesn't pop.
That's even.
Okay, but that's only because the balloon isn't big enough. How do I know the pressure inside and the pressure outside of the balloon are equal right now?
Because the air isn't trying to escape or go in.
Okay, let me rephrase the question. If there were high pressure inside the balloon and low pressure around it, what would be happening? The balloon would be getting bigger. If there were low pressure inside the balloon and high pressure outside, what would be happening?
Shrinking.
The balloon would be shrinking. How do I know the pressures are equal? It's not doing either one of those. It's not getting bigger, which means there's no high pressure inside, and it's not getting any smaller, which means it's not low pressure. So pressure has not changed. I understand your point, Vic, but it has not. Okay? It has not. I did change the amount of air in here, correct? Which variable is that? And the amount of gas. What changed because of it? Guys,
The volume.
original? Now,
The volume.
the volume changed. The volume changed. Welcome to Avogadro's Law. Avogadro's Law says the more gas you put in something, the more volume increases. That might be the biggest no-brainer gas law of all. You blow up a balloon and you've demonstrated Avogadro's Law. What kind of relationship?
It's direct
Why?
because you're just adding in more, and then after that, and then
You did a Seinfeld great one there. You just added a and then yeah. Go.
Because the amount of gas and volume both increase.
Thank you. The more air I put in here, what happens to the balloon? It gets bigger. So the more gas I put in, the more the volume increases. That's Avogadro's Law. That is Avogadro's Law, ladies and gentlemen. Avogadro's Law says the volume of a gas will vary directly, meaning a direct relationship, to the amount of gas. But what are we holding constant? Pressure and temperature. Pressure and temperature. Now those are held constant. Guess what? What kind of mathematical relationship would volume and N, or amount of gas, be in? What would we do to them mathematically? Add, subtract, multiply, or divide. Think carefully. Think of other direct relationships. Okay, let's go back.
Divide.
What?
Divide.
Exactly. Every direct relationship. Charles, Gay-Lussac's, Avogadro's, all involve division. Because that's what we do with direct relationships. So what would the graph look like? Straight line going up. Straight line going up. That doesn't change. That's what a direct relationship is. A line that's going up. A constant one means that it's going to be straight. I don't care if we look at the formula. We could tell inverse or direct. I don't care if we look at the graph. We could tell inverse or direct. We could tell constant or non-constant. Why? It doesn't change. In a direct relationship, the graph goes up. In a constant relationship, the line is straight. So, what would the formula look like here?
V divided by n equals.
V divided by n equals k. By the way, have you noticed where V is in every formula?
Yeah.
Where?
Top.
On the top. Have you noticed where pressure is in every formula? Pressure is always.
Bottom.
Really? Look at the last gas law we did.
Oh, on the end.
How can you be in the middle of a fraction? You're either on top or the bottom. Where is pressure always? On top. Where is temperature always? On the bottom. For consistency, ladies and gentlemen, in gas laws, volume is always on the top in every gas law. Pressure is always on the top in every gas law. Even Boyle's law is PV, right? Both numbers, nothing underneath. So it's like they're both on top. Temperature is always on the bottom. N is always going to be on the bottom. So you could say V1 over N1 equals V2 over N2. We can say that. Okay? Still a direct relationship, meaning if volume goes up, what happens to the amount of gas? Goes up as well. If volume goes down, what happens to the amount of gas? Goes down. The amount of gas goes up. The volume goes up. The amount of gas goes down. Volume goes down. Questions? Now we have taken and made it so that the amount of gas inside the balloon has gone
Bye-bye.
down. What happened to the volume of the balloon?
It popped.
Went down. Went down. By the way, ladies and gentlemen, that is the only good use for a balloon in the world today. Is to pop it and startle people and enjoy that people's reactions. Questions?
I can't remember.
Yes, go Faith.